So our next speaker is Dr. Michael Mühlebach. He's a former ETH alumni. He obtained a PhD degree at the Institute for Dynamic Systems and Control under the supervision of Professor Raffaello D'Andrea. Then he joined the group of Professor Michael I. Jordan at the University of California, Berkeley as a postdoctoral researcher. Since 2021, he started as an independent group leader at the Max Planck Institute of Intelligent Systems in Tübingen. He is interested in a wide variety of subjects, including machine learning, dynamic systems, and optimization. And he received several awards, among which the ETH Medal and the Hilti Prize for Innovation Research for his PhD thesis, a Branko Weiss Fellowship, and an Emmy Noether Fellowship. Today, he's going to share his take on optimization with momentum and constraints from a dynamical systems perspective. Michael, the floor is yours.
Well, yeah, thank you very much for the kind introduction. Hi, everyone. Thank you all for inviting me and being here. And yes, today I will talk about optimization. So why do I care about optimization? Well, on a fundamental level, optimization provides us with a framework for rational decision making. And as a result, I'm convinced that optimization is driving and will drive science, engineering, and technology. And here's three potential applications. So in computer-aided diagnosis, medical doctors are supported by powerful machine learning algorithms, and these learning algorithms are trained with optimization. In air traffic control, you could use optimization algorithms to schedule flights in order to, for example, mitigate the propagation of delays and reduce fuel consumption. And in statistical inference, you can use optimization to fit statistical models through some empirical data, and this has applications in climate science or weather predictions, for example. Now, in my own research, I encountered optimization with robotic systems. And so, for example, here, together with a student, we set out and we wanted to push the boundaries of what's doable with quadrotors. And we used here optimization for numerically solving optimal control problems, and we decided to perform this flip, a maneuver which has never been done before. And the important thing to notice here is that the pendulum is not attached to the quad, but the quad has to bounce this pendulum at every time. Here's another example where we used optimization for the design of the system. And this is very recent and joint work with Matthias Hover and also Raf. So this is a balancing robot, and it's a very, very special kind of balancing robot. So here it just balances on the tip, and we added a mirror to exemplify that there's no gimmicks involved. And the special thing about this robot, it has a single reaction wheel to balance. And so to all control engineers, it has one actuation, one single reaction wheel, and it's able to stabilize both tilt axes. And the way we can do that is by designing the system so that it has this very special inertia, which separates the time constants of the tilt dynamics. And so nevertheless, this is a highly underactuated system. We have about 10 degrees of freedom, which are unstable and marginally stable, and we make it, we can stabilize it. And the key to the success was a careful design of the system using optimization. Some other research project is this robot here. So this is a robotic arm, and the special thing about this robotic arm is actuated by pneumatic artificial muscles. And these muscles behave in very nonlinear ways, and so it's difficult to have a very accurate first principle model of these systems, of these muscles. And we use the robot in a playful manner and play ping pong. And here we use optimization in an online learning framework. And so this robot learns from over time and improves its trajectory tracking performance over time. So with all of this, you may now wonder, well, optimization is used in all of these cool robotic applications and outside in other applications as well. So what are the challenges? And I think one of the key challenges in optimization is how can we deal with very large-scale problems? And how can we take or tailor an optimization algorithm to a specific type of problem? So that refers to the non-intuitive parameter tuning. And then, of course, sometimes you have non-convexity, and sometimes you have constraints as Tamir showed us. And these might be non-convex or semi-infinite, and this is highly challenging. And at the heart of all of this is the difficulty that an optimization algorithm should not perform well on a single function, but on a whole class of functions. And in the following 40 minutes or so, I will try to address some of these challenges. So I will talk about optimization algorithms with momentum, and I will try to make a sense of how we can adapt the algorithm to a specific problem at hand. And then in the second part of my talk, I will focus on constraints. Yes, so let's get started. And when we talk about optimization with momentum, I think it's best to start with a simple numerical experiment. And so here I randomly generated a quadratic program, and I compared two methods, an accelerated method, which leads to the black curve, and the non-accelerated, the standard gradient method, which leads to the red curve. And as you can see, the accelerated method beats the gradient method by roughly an order of magnitude. And both methods have the same complexity per iteration. So this is an immense speed up, and it might make the difference between waiting for a few hours and waiting for a day. And while this phenomenon has been around or known in optimization for quite a while now, and I think it's also one of the key findings, really understanding its scope has been a mystery and a difficulty still up to this point. And so let me introduce some mathematical notation. So we're interested in minimizing the objective f. So we're interested in finding the x star. And in order to fix the ideas, and in order to start off, I focus on the case where f is smooth and strongly convex. So it means that it satisfies this inequality here for all x and x bar. And we'll see that essentially all of the ideas and all of the approaches that I will show you directly translate to the non-convex case. But it will be important, I think, for fixing the ideas to first look at this case. And in particular, there's two constants here which are important. So there's the L, the Lipschitz constant of the gradient, and then there's kappa here. And kappa is the condition number. And so what does the condition number tell you? Well, if kappa is close to 1, this means that the function f has round level sets. So the function f looks the same across all directions. If kappa is very large, this means that the level sets are very distorted. They're more like elongated ellipsoids. And this will be important to keep in mind. And with the notation in place, I can now state both algorithms. So there's gradient descent on top, and there's accelerated gradient descent. So we used a version from Nesterov with a constant step size. And the interesting thing about this method here is that it evaluates the gradient at a position which is off, right? And it has also these two constants, d and beta, and these are chosen as a function of kappa here. And the theory, the classical theory, tells you that if you precisely choose the constants in this way, and if you have a convex function, then your algorithm on the bottom, the accelerated one, converges linearly at a rate which scales with the square root of kappa, right? And this is in sharp contrast to gradient descent, which also converges linearly, but where the rate scales with 1 over kappa. And if kappa is large, say 20, 30, or 100, then this difference is significant, and this is what you can see on the left. This explains the important empirical performance benefits on the left. And so in the next few slides, I would like to illustrate and discuss with you what is really the mechanism that leads to this faster convergence compared to the standard gradient descent convergence. And I will use a dynamical systems point of view, which connects to this workshop. And to underline that this is a difficult problem, here's a quote from Arkady Nemirovsky, who says, "Let me add some words about the Nesterov method. As it is, it looks like an analytical trick. I would be happy to present you with a geometrical explanation, but I don't know it. So we'll provide you with dynamical systems explanation." And that's what we're going to do. And so first, we'll focus on this Nesterov method, and then in a second step, we'll characterize more broadly the mechanism that leads to this fast convergence. And finally, in the third part of my talk, I will talk about constraints, so optimization with nonlinear constraints. And it turns out that you can take this ODE here, this dynamical system, and discretize it with a well-known scheme called the Semiimplicit Oil Scheme. And with a time step of 1, you obtain the method that I showed you on the last slide, the last slide, yeah. And so this brings a connection of this ODE to the discrete equation or the discrete algorithm. And I will provide you with an interpretation of both the continuous time ODE as well as the discretization. But because by training I'm an engineer, I would like to start with the ODE. And so we can bring this ODE in first order form. So we can, in a way, single out here the potential forces, which you could think of as spring. And then we have the non-potential forces, F and P, and these take the following form. And you can make sense of these by dividing them into 2 parts. And the first part here is just a constant times the velocity. So P is the momentum or velocity. And so what this means, it's damping, which is the same across all directions. So I call this isotropic damping. And the second part of the damping term here, you can view that as a local average. So here that's a Hessian of the objective function. So it's a local average over the Hessian, a local average of the curvature. And this local average determines on the current velocity, the current momentum, as well as this constant beta, right? And we can now make sense of the choice of D and beta and compare it to the damping that we have here, right? And so in particular, if kappa is close to 1, then 2D is close to 1, and so the emphasis lies on this first term, which intuitively makes sense. If we have an isotropic, a problem which is isotropic, then it's the same across all directions, and there's no need for adding this curvature-dependent damping term. Now, as kappa increases, essentially the emphasis, so 2D goes down and beta goes to 1, and the emphasis is therefore on this term, lies on this term here. And in continuous time, it's extremely straightforward to talk about stability and to guarantee that we converge to stationary points. And so the way we can do this is we can look at the energy function and ensure that the energy decays along trajectories. And this works in the convex case. In the non-convex case, it works in a very similar manner. So that gives you an interpretation of the continuous time dynamics. Now let's look at the discretization. So we can take the ODE, apply the semi-implicit Euler discretization, and we obtain Nesterov's method. Now, the thing about this discretization is that you can divide it into 2 parts. And the first part here, and these 2 parts are applied in alternating fashion. And the first part is a simple update of the velocity or the momentum here with the non-potential forces. And so you can view this as a dissipation step. And the second part here, that's the part here, that's a very well-known integration scheme. And this part is only based on the underlying conservative part of the dynamics, the Hamiltonian part. And indeed, it's a structure-preserving integration step, which is the symplectic Euler step. So the intuition here is really that this is dissipation and this is energy conservation, but it will be a slightly modified energy function. And we'll use that also in our analysis. Okay, and so the intuition is that you alternate between dissipation and energy conservation. Okay, and so that ends the first part. I hope that I could provide you a dynamical systems way of thinking of this Nesterov algorithm. And now in the second part, I would like to characterize more broadly what are the necessary ingredients to really end up with this fast convergence rate. And in particular, is this funky evaluation of the gradient here, is that really needed? And I will, in line with the workshop, I would like to approach this from a dynamical systems point of view, and so view an algorithm really as a dynamical system. And what this does is I would like to distinguish between a stability analysis and the rate analysis. So let's focus first on the stability analysis. And let's start again to fix ourselves to some concrete example. Let's look at this non-convex function that has 2 local minima and a local maximum here. And so we can initialize our algorithm from various initial conditions. And as you can see, depending on where we initialize, we either converge to the left local minimum or to the right one. Right? And now, by a stability analysis, I mean, can we characterize the regions of attraction of each of these equilibria? And one way to do this is, well, we can add more trajectories, and then we can look at the energy function. And clearly, if we initialize our system, because we know energy is dissipated along trajectories, if we initialize our system with a low energy level, so that we're trapped on this left, for example, in this left valley, then we know we get trapped here and we converge to the left equilibrium. And the same applies if we start on the right. However, if our energy level increases, at a certain point, we hit the saddle here, and then essentially trajectories can cross. Right? And so, in a way, mathematically, in fancy language, the critical points determine the topology of the level sets. And what we can do is we can look at the level set that corresponds to the saddle, and this divides the state space in different parts. And we know that, okay, if we start in this region, we're going to converge to the first equilibrium. If we start here, we're going to converge to the second equilibrium. So this answers in part, or to some extent, the stability question, right, and characterizing regions of attractions. Now, let's look at the rate. So by getting a rate, what do we want? We would like to characterize the distance, QP, to a local minimum. And we would like to get a bound that has a constant here, the initial distance, times something that is exponentially decaying. And I think it's, again, interesting and useful to look at the concrete example. So we have trajectories here, and we would like to fit this bound. So let's try it. We have C 2.5 and alpha 0.2, and this seems like a reasonable bound. However, we can also increase C and increase alpha, and this also looks like a reasonable bound. So because we're dealing here, we're working on a compact time interval, we can always increase C and increase alpha. Right? So what this tells us is this rate alpha is only determined by the behavior for very, very large t. And because we have stability for very large times t, we're close to the local minimum. And so the upshot of all of this is that the global shape of the objective function determines the regions of attraction, the stability properties. But the rate is determined by the local properties, right? And we can have a formal proposition that summarizes these results, which is well known in the dynamical systems community. So if we have dynamics which are twice continuously differentiable, if we have an asymptotically stable equilibrium with a certain region of attraction, and if we have linearized dynamics that converge at this rate, then for a compact set in the region of attraction, we can find a modified constant C tilde so that we converge still at the same rate. And the way this works is the following. So we exploit the continuous dependence of the initial conditions and the fact that A is compact. And both of these ingredients guarantee you that after a finite time t, you'll be arbitrarily close to a local minimum. And once you're close to a local minimum, the dynamics will be governed by the first order approximation. And so that's how the result can be established. But for optimization, it provides you with a very handy tool for analysis, right? Because in continuous time, we said, okay, we already looked at stability, we looked at the energy function, and we were characterizing how the regions of attraction and the stability of the different equilibria. We can now determine the rate by doing an eigenvalue analysis, and if we do so, we have this constant h that pops up, and this constant h is the local curvature at the local minimum. And so we can say, for example, okay, the function is locally strongly convex, so which means that h varies from 1 over kappa to 1, and so we have to figure out how the eigenvalues change. And we can do this, and so, for example, in the case where beta is equal to 0, we can divide between two regimes, a small damping regime and a large damping regime. And if we're in a small damping regime, then the eigenvalues here are complex conjugates. And as we increase the damping, at some point they become real. But in any case, we can guarantee that if we want to have this fast mode of convergence, the damping should better scale with 1 over square root of kappa. So if the damping is too little or the damping is too large, there's no acceleration, which is going to happen. And the same can be done with beta not equal to 0. The difference is that if beta is not equal to 0, this will essentially bend, add some negative real parts to the eigenvalues, but the story is essentially the same. So we conclude that as long as our damping parameters d and beta scale with the square root of kappa, we have accelerated convergence of this continuous time model. Now let's see if we can translate this to discrete time, because that's where really things get interesting. And the way we're going to approach this is exactly by applying the same train of thoughts. And so we're exploiting the fact that we can divide into this dissipation step and into this symplectic step. And for this symplectic step, we can use a tool called backwards error analysis, and we can come up with a modified energy function, which is exactly or almost exactly preserved over this step. And we can use this modified energy function for stability analysis, much like in the same way we use the original energy function for stability analysis in the continuous time case. And so here's the statement of our proposition. And we have here this perturbed energy function, which over one step of the Euler discretization, so the semi-implicit Euler discretization of only the conservative part of the dynamics. So this is only one step of that is based on the conservative part of the dynamics. We obtain this bound here. So we obtain 8.5 t equals to something divided by t. And the thing about this bound is that it gets astronomically small if t is, say, 0.01. Then this gets to 10 to the minus 33, because in the exponent here we have this divided by t. And what this means is that essentially it's almost exactly preserved. So we're going to just neglect the contribution over this step. And more importantly, we were able to derive bounds that relate the original energy function with this perturbed energy function, and these are useful then for stability analysis. And people may wonder now, if you look at this, you may wonder, okay, why does this guy have explicit constants? So why does he know that this is 0.023 and so on? And what you have to notice here is that we divided by the Lipschitz constant of the gradient, right? So we normalized the time constants of the dynamics. And this allows us to give these explicit constants. So in the general case, you would have everything multiplied times L. But it's, yeah. Okay, and we can now follow the same train of thought. We can use this perturbed energy function for stability analysis, and then we can look at a linearization for determining the rate. Now, we're in discrete time, so we have to look at the absolute value of the eigenvalues, but essentially the conclusion remains the same. So the statement here is that as long as you choose your damping parameters to scale roughly with 1 over square root of kappa, you'll obtain an algorithm where you can find a time constant, a time step t small enough, but independent of kappa, so that you obtain this fast rate of convergence, which scales with the square root of kappa, so which means that you have acceleration. And one interesting corollary of this is that you can set beta equals to 0, and you still obtain an accelerated algorithm. So this funky evaluation of the gradient, which many people believe that this was at the heart of Nesterov, is not needed. So I find this very interesting. And the key to this is really to exploit backwards error analysis to get this perturbed energy function that is almost exactly preserved over the one part of the discretization. Yes, because this, in a way, allows you for a principled way of synthesizing a Lyapunov function. Okay, and with that, I would like to conclude the first part of my talk. How much time do I have left? You have about 20 minutes. Okay, that's great. Okay, so the second part of my talk, I would like to share some thoughts about constraint optimization. So I think constraints will be increasingly important, in particular in machine learning. We saw some applications in reinforcement learning, and more general, constraints allow you to incorporate prior knowledge into machine learning, and this could help with making your algorithms to have a lower sample complexity, or it might help for ensuring safety and reliability. Now, if we look at constraint optimization, I think it makes sense to divide between different scenarios. And one scenario is certainly where you have a clear structure in your constraints. So where you're optimizing maybe over a probability simplex or a low-dimensional hyperplane or a norm ball. And in these cases, you can often do projections or Frank-Wolf updates in closed form. So there we have very efficient algorithms that can scale well with the problem size. However, if we move outside of the structured constraints, which I call unstructured constraints, then typically people rely on interior point methods or sequential quadratic programming. And for me, I was wondering, well, can we contribute something here, which is of first order but can handle general constraints? And the idea would be, again, which is in line with the theme of this workshop, to exploit analogies between dynamical systems and mechanical systems and optimization. And so on the left, we have an optimization problem. So I changed cost function from F to V because I want to distinguish the previous results from the results here. Here we are dealing with constraints. And the idea is that you can construct this non-smooth mechanical system, second order, for example, and this is such that the equilibria correspond to the stationary points of the underlying optimization problem. So in a way, what you can do is you can simulate the mechanical system and wait until it reaches essentially an equilibrium, and then you know by construction this equilibrium corresponds to the solution of an underlying optimization problem. And let's look at the algorithmic consequences. And I would like to contrast this to projection-based approaches. So in projection-based approaches, we take a step along the gradient, and then we project onto the feasible set. And as you can imagine, if the feasible set is non-convex or non-linear, this projection might be very difficult to evaluate. Now, what we're going to do next, or in this dynamical systems from this dynamical systems point of view, we're going to add a constraint force, right? And what we can do is we can lift position constraints to velocity constraints. So instead of saying, okay, we're constraining that x of t should remain in the set C, we can say, okay, in continuous time at least, we can equivalently say that the forward velocity should be in the tangent cone of the set C at the current point x. Right? And so in a way, mechanically speaking, you're lifting a position constraint to a velocity constraint. And what this leads to is that this tangent cone, you could think of this as a local and linear approximation of the feasible set. And so here's some more examples. So here we have a non-convex set, and the tangent cone at x2 is just given by this half space. The tangent cone at x1 is given essentially by the cone that is spanned by these two rays. Right? So in each case, you have a local approximation, which is also linear and sparse. The only trouble is that if you move from continuous time to discrete time, you take steps of finite lengths. And so if you impose the condition that you constrain your velocity, the forward increment, to be in the tangent cone, then you might very well step out, right? Because you're simply considering only a first-order approximation of your feasible set. And so the question is how to deal with that. And we approach this in the following way. There might be other options, certainly, which could also lead to solutions. But we thought one of the easiest way to do this is to simply add this additional term here, which measures how much the constraint I is violated, and it adds a restitution coefficient, alpha. So alpha, in a way, is a tuning variable, and we just add this additional term. And what this does, if you're outside the feasible set, it tells you, okay, your forward velocity should be directed towards the feasible set. So it points you a little bit towards the feasible set. But the important thing to realize is that we're still only considering, at each x, we're only considering constraints which are violated. So we're not anticipating any constraints. We're just looking at which constraints are violated, and we're using these to form the set V alpha, which you should still interpret as a velocity constraint, a constraint on the forward increment. And now the question is, can we prove any convergence guarantees? And so I worked hard on this for the last year or so, and finally I was able to get a convergence result. So there are several possible setups. In one case, we assume f, the function v, is strongly convex, and there we can guarantee that even with a fixed step size, performing fixed steps of this gradient-based approach, we can converge to the minimum of the constraint problem. And the interesting thing is that the condition on the step size here is very closely related to the unconstrained case. The only difference is that this constant LL here is now a Lipschitz constant that relates to the corresponding Lagrangian. So in the unconstrained case, you simply have the Lipschitz constant of the gradient. Here you have a constant that relates to the Lipschitz constant of the gradient of a Lagrange function. So it seems a nice or intuitive generalization from the unconstrained to the constrained case. And we can also look at the non-convex case, which is in particular interesting for applications. But there, in order to prove convergence, we need some sort of diminishing step size. So there we can prove convergence, but we need a diminishing step size. And for the convex case, we were also able to derive rates. So asymptotically, we obtain linear rates. Yeah, so that's it. And how much time do I still have? 8 minutes. Okay, so I can give you some insights. So here I just want to emphasize quickly the challenges that arise with the analysis of this gradient-based algorithm. And I would like to illustrate this on a very, very simple toy problem. So here we have the objective, which is just a simple quadratic, and our feasible set is just all real numbers between 0 and 2, which I showed with this green bar. And now the question is, how does this algorithm work on this simple problem? And so here I just added the definition of the algorithm. So we compute this velocity function as a function of x. And here's how the velocity function looks like. And let's start by looking at the case where we're feasible. So if we're feasible, essentially the constraint is absent, and so v is just a negative gradient. Now, if we're outside of the feasible set, if x is greater than 2, then we have one constraint violated. So what this velocity constraint tells us, okay, we should move to the left with at least this amount alpha g2, which is plotted here. But because this amount is lower than the negative gradient, we just stick to the negative gradient. Right? So here for numbers greater than 0, we just have the negative gradient. Now, if we have a constraint violation here of the first constraint, then essentially v is no longer the negative gradient, but is adapted over this regime, right? And the challenge, or what's interesting about this function, is that clearly v jumps, right? So the dynamics are discontinuous. This map v is discontinuous, so you have the jump here. And if you now run this algorithm, you see that if you start from positive x, you will go along the negative gradient, and then we'll jump to the infeasible region and then approach from the right. On the other hand, if you start from the infeasible region, you will approach from the right, right? And the key for understanding that you indeed have convergence is to think of this boundary from feasible to infeasible as a semi-permeable membrane that essentially allows trajectories to go from feasible to infeasible, but not the other way around. And that was the key to the analysis. And I would just emphasize here that a simple enumeration of the different cases does not lead anywhere. So you could be tempted at first to just think about, okay, we can look at different cases where different number of constraints are active, but this is just hopeless. So in our two-dimensional case, we had 2 different cases, but then if you step it up, in 2 dimensions, you have 8 different cases, and in n dimension, it just blows up exponentially. So there's really no hope. Yeah. And we also tried it out in practice. So we tried, for example, to run this on randomly generated quadratic programs, and we compared it to an interior pointer method, so the state-of-the-art method CVX-opt. And we observed that we have indeed a different scaling with the dimension. So our algorithm was somewhat scaling with n to the power of 2, whereas the traditional method or the interior point method was scaling with n to the power of 3. And so that I found very, very interesting. And this motivated me to actually do the theoretical analysis. And we also did tests on randomly generated trust region problems, and we're currently looking into problems that arise in computational chemistry. So maybe in a year I can give you an update on these. But for now, I would like to conclude. The first part of my talk essentially tried to make sense of these accelerated algorithms and show that we can understand this by viewing these as continuous time, second-order dynamics, plus a symplectic discretization of the underlying conservative part of the system. And in the second part of the talk, I showed you a new approach to essentially lift position constraints to velocity constraints and show that you still obtain convergence for the resulting algorithms. And with that, I would like to thank my past mentors for essentially shaping my scientific thinking in fundamental ways, as well as the excellent funding that I received from Emmy Noether and Branko Weiss. And last but not least, all my students and collaborators. So here's not a complete picture, but this is just a summary of my group that I started at the Max Planck. With that, I would like to thank you very much for your attention. And I'm happy to take questions.
Thank you, Michael. The floor is open for questions.
So, thanks for the very nice presentation. Of course, we are super interested in optimization with constraints, for example, for physics-informed neural networks. You would typically add a cost function there if you violate some of the differential equations that you would like to have satisfied. Now, if you would apply your method to this, how would you expect it could perform?
Yes, so that's a very good question. And I think I hope to give you, in a way, a physics-based answer. So yes, a common approach is to regularize and to add a penalty for constraint violation. But then the question is, then you typically need to tweak the penalty, and you need to make the penalty very large so that you return to the feasible set. And this leads to sort of dynamics that evolve at different timescales. And this is therefore very challenging for the discretization. And so if you make your penalty very large, you will run into the problem of trying to make your penalty very large, but then you need to make small steps for your algorithm to converge. And so, in a way, here we have this approximation, but we do projections. So we include this velocity constraint. We do these projections on the local sparse approximations. So we don't run into this problem of requiring some sort of penalty where we have a parameter that we need to essentially increase. Yeah. I hope that answers your question. Yeah.
Other questions?
Thanks a lot for the presentation, very nice. I was just, we were a technical curiosity, like when you have this velocity constraint, and these are perfectly valid in a non-convex setting, right? When you move to the discrete time version of that, you seem to have a stronger result for the convex case.
Stronger result for the convex case. So I used diminishing step sizes.
Okay.
Right? Whereas in the convex case, we don't need diminishing step sizes.
Here, right. Yeah.
We can use a constant step size. And analysis is I would say, fundamentally easier if you have a diminishing step size. Because in the long run, it allows you to easily prove that you're going to converge to the feasible set. Yeah. I must say, this is in a way a little bit an informal summary. So we need additional assumptions so we're making, for example, the assumption that our feasible set is compact. And in the non-convex case, we're also assuming that we have bounded velocities. But you can get bounded velocities by slightly modifying the algorithm and imposing a large bound. And then you can argue that if in the long run, eventually, you will never clip or never have this bound occur. Right.
Yeah,
so for the precise results, you have to look at the paper.
Sure. Yeah. I was just trying to understand if that's a limitation in a way of how you can actually prove these results, or if you encountered cases where the non-convexity actually prevents from using this velocity constraint in the discrete time.
Yeah.
Or if in general you can fix it just by taking a
I think so. personally, I think it's remarkable that you can work with a constant step size. And this will, I don't think you will be able to get a guarantee for the non-convex setting with a constant step size, because you can easily end up in situations where you oscillate back and forth. And notice also that because you're never anticipating constraints, if you're moving relatively fast, if you have a high gradient, then you can easily pass through a constraint without noticing it, for example, which could all happen in the non-convex setting. And this tells you that for the non-convex setting, you really need a diminishing step size. Yeah.
Great, thanks a lot.
Other questions? Okay, I have one myself that I wanted to ask before. So this detour that you take to continuous time dynamical systems to explain, to give this geometric interpretation for the Nesterov methods, answers these open questions of Nemirovsky that was formulated many years ago.
I don't know. You have to ask him. I'm not claiming it. It just gives a different perspective. Yeah.
Okay.
I'm not sure if he had that sort of answer in mind. Probably not.
It will be interesting to hear his opinion. But my question is there any other advantage in taking this detour, for example, in stability guarantees or bounds for the step sizes?
So, well, I can answer this from a personal perspective. See, I was taught here Nesterov's method, and we had like a convergence proof of like 3 pages with all just linear algebra. And the professor said, well, here's the proof. I don't know really how it works, but that's the proof. And so I wanted to figure out in a way and get an intuitive understanding for why this is a reasonable thing to do, such an algorithm, and why, at least for me, it will make sense to have this fast convergence rate. And I think what this perspective brings to the table is that it might allow you to understand the algorithm beyond the just narrow setting that you're concerned with in theoretical analysis. See, if in theory you say, okay, let's assume we have a convex function or a strongly convex function, so on, and then you prove a rate for exactly these algorithm parameters. And I think this perspective here allows you to get a more qualitative understanding of how the algorithm behaves, right? For example, if you have maybe a non-convex function, maybe maybe you choose the algorithm parameters slightly differently, and so on. Maybe you have noise, and so on. And I think this provides you a more qualitative understanding. Yeah.
Thank you.
Yeah.
Other questions? Yes, Dominic.
So for the second part, when you asked about when you introduce kind of the non-smoothness, right? You're pretty clearly giving up stability, right? You have convergence of the algorithm, but you're giving up stability, right? Those aren't the same thing.
Yes.
So, obviously if you have disturbances or something, you're kind of screwed, right? It'd be very hard to use this in any kind of problem with noise, right? But just in your numerical experience, does this affect, let's say, if you've got round-off error or something coming from, let's say, just from the computer?
Yes,
does it ever give you trouble?
It's a very good point. And when people see this, you should exactly ask this, yes. And, well, there's 2 answers to this. One answer is that you can slightly allow for, say, you can slightly extend what you consider, slightly extend the set IX. So what you consider to be a violated constraint. And what this will do, it will put essentially this jump a little bit out to the right. So you'll have this jump occurring here, right? And then in a sense, you can deal with numerical round-off errors. So that's not an issue that I experienced. And now to your answer to your question in the stochastic setting, I think it even works in the stochastic setting. The key is really to have diminishing step sizes. And this gives you this averaging effect, and that gets you, and it allows you to get away with it, yes.
So it'll jump, but it'll jump by smaller and smaller and smaller
Exactly.
amounts.
The jumps will be smaller and smaller and smaller. Exactly.
Thanks.
Yeah.
Other questions? Yeah.
So I actually have 2 questions. So you mentioned coming back to this dynamic system perspective of Nesterov's acceleration. So you mentioned this result also extends to like when you have stochastic noise or when your problem is not necessarily convex. But we also know on the other hand, momentum type ideas does not necessarily give you any provable benefits for non-convex optimization or for stochastic optimization. Like, what's your take on that? My second follow-up question is, oftentimes momentum is combined with this type of adaptive methods like ADAN, RMS prop in training neural networks. Like, how would this type of dynamic systems perspective be adapted to those adaptive methods, like the state of the art? Yeah, thank you.
Yeah, these are great questions. Yes, so one thing to realize is that you have to be very careful about the type of convergence or the type of setting you're dealing with. And so when you have non-convex optimization, typically people say, okay, you use SGD, right? And then you can show, okay, SGD under certain circumstances is unimprovable. And the thing is that the analysis relies on, again, a sort of averaging effect. So you have two effects. You have, in a way, the deterministic convergence rate, and then you have the influence of noise, right? And usually you want to take your step size smaller and smaller or do some averaging to bound the influence of the noise, right? And in that sense, SGD is unimprovable. But with momentum and with the accelerated parts, you can still improve on the deterministic part of this convergence bound. So it depends on the setting I think you're in. And I think this dynamical systems perspective really allows you to understand these different nuances. Yeah.
Other questions? Then we can close it here. Let's thank Michael once again.
Thank you.